Good morning, sir.
Yeah, so today I will start vector integration. So the idea of integration already we have for a function of single variable and probably function of two variables as well as three variables, double integration and triple integration. That idea you have already. So now we just want to translate that idea for the uh, for the functions, vector functions actually, and we call these integration as vector integration. Okay, so suppose we have a vector function Ru. So R is thick, so therefore it is a vector function. It has three different components, and it is a function of scalar variable u. Only one scalar variable. Note that scalar variable u. And let us also suppose the vector A is the differentiation or derivative of the uh, vector function Ru. So that is A is equal to A is a vector. A is equal to ddu of Ru, and you know how to find this ddu by now. So we have to perform the differentiation component wise. Okay, then we'll get the derivative, and I, j, k they are constants. So therefore we'll get a vector A. And if this happens, then the indefinite integration of A with respect to u, the independent variable u, independent scalar variable u, is given by Ru plus C. C is a arbitrary vector constant.
Sir,
Okay,
sorry
so
to interrupt, sir. There is some noise in the background. Can you hear, sir? Can you mute?
acha,
I
so
mean, from
yeah,
the
yeah,
participants.
understand. Yeah, mute all. Yeah, so this is the typical antiderivative technique. So we have a function, after differentiation we got some another function, and if we perform the integration operation we'll get back the original function together with some arbitrary constant. So idea is similar. Okay, the idea of indefinite integration we have as antiderivative or inverse process of derivative um, directly can be directly translated for vector functions in this way. Okay, I will discuss some examples. And if you if we know the problem, if we know the components, different components of Ru, suppose different components of Au, suppose Au is equal to A1u, that is the first component, or x component, I vector, I unit vector plus A2u, j plus A3u k, then we can perform the integration component wise. And this is simply like the indefinite integration of a function of single variable. And if you add this integration, after the integration, if you add all the terms after the integration, you will get the vector Ru. Okay, plus some additive constant, plus some additive constant. Now, how definite integration can be evaluated? The technique is similar. You just find the indefinite integration Ru and then Rub minus Ra. So relevant theorems and other things are similar, and I have not included those theorems over here. Okay, this is quite straightforward. Now some simple examples. Suppose Au is equal to the given vector function. The given vector function u square I plus u minus 1j plus minus 3uk. Then, so can you see the slide, or it has stopped sharing?
No, sir, we can't see.
No, sir, we can see, sir.
Okay. Okay, thank you.
It's fine.
So u square I plus u minus 1j minus 3uk. Then we have to find the indefinite integration of the vector Au, which is a function of the scalar variable u. So we will just, and then we have to find the definite integration
Excuse me,
from
sir.
2 to, yes,
Sir, can you please show the previous slide once?
yeah, this one.
Okay, sir. Thank you, sir.
Okay. Yeah, so let us evaluate this, and it will just natural. This extension is natural, you can understand. U square I, let me just solve it. So what is AU? That is given AU is equal to U square I minus
Plus
1 minus U
plus
J
u minus 1 plus
plus
u
1
u minus
U
1
minus
U
1.
minus 1
Same.
initial correct था.
minus
3 uk cap
3 UK.
okay. So therefore we have to find the integration of AU, indefinite integration with respect to du. Then we will perform the integration component wise. I U square du plus U minus 1 J U minus 1 integration du plus a minus k 3k rather U du, and this is equal to I U q by 3 plus j U square by 2 minus U minus is vector. That is the difference. That is the only difference. So this is how we can evaluate indefinite integration, and if we are interested to evaluate this definite integration AU du, this is equal to, simply we have to put the limit on this function, on this vector function, plus j U square by 2 U square by 2 minus U minus 3 U square by 2 k, and we have to put the limits 2 and 3. First we will put 3 and then you will put 2 and subtract. So if we put 3, then what we will get? 9i
19
by 3
27 by 3, so 9i, and here 9 by 2 minus 3, 9 by 2 minus 3 is
3 by 2.
yeah, so plus 3 by 2 j, and here 27 by 2 minus 27 by 2 k minus, if we put 2, 8 by
8 by
3 i,
3.
8 by 3 I, and 4 by 2, so 4 by 2 is 2,
0.
this is 0, there will be no j component, minus 6 k,
60.
and if you subtract this you will get the definite integration. So this is as simple as this. Now we will introduce a very a little bit new concept which is known as line integral. Okay, which is known as line integral, and before defining this line integral we have to recall the concept, of integration of a function of single variable. So what is the basic concept? So that basic concept we will translate for a vector function, and we will define line integral. So what is there? What are the basic ingredients? If whenever we encounter this symbol fx dx, and we try to evaluate this from the first principle or from the definition, then what we do? So basic ingredients, yeah, so A to B, this is the first thing. This is the region of integration. Okay. And let us suppose this is our A and B, x is equal to A, 0 to x, and x is equal to B, and graph of the function fx is something like this. Okay. This is y equal to fx, and we have a function which is defined in the region AB. And then how do we calculate this? What is the definition? This is equal to, so we basically first divide the interval B to A into finite number of subintervals. Okay, by introducing the points x0 is equal to say A, x1, then x2, so on, xn is equal to B, and xi is equal to A plus I minus 1 into h. And what is your h? H is equal to B minus A by n. Okay. So this is the first thing we do. First, we divide the region of integration, which is the closed interval AB, into finite parts. Okay, by introducing n minus 1 points between the numbers A and B, between these two. Okay, so this, and for simple textbook problems, what we do, we take equal intervals. Okay, we put the points x1, x2 up to xn minus 1 in equal intervals. This is your x0 and then x1, x2, this is your x2, so on. And the last one, xn minus 1, last but 1. And last one is xn, which is equal to b. So basically we introduce n minus 1 number of points, equidistant points between A and B. And then what we do, we take, for textbook problems, we take either we evaluate the value of the function in the left of each subinterval. Okay, so this is the definition. Let us have a look at it. So what we do, A plus RH into H summation R is equal to either 0 to 1, 0 to n minus 1, or we consider the sum R equal to 1 to n f A plus RH into H. So this is called left hand approximation and this one is right hand approximation. And if this limit H tends to 0 exists uniquely, we call that value as the integration of fx over the interval AB. Okay, so both can be shown that they are equal dx. Okay, and if you consider the general definition of Riemann integration, this is called Riemann integration. Okay, general definition of Riemann integration, it is not necessary that we have to consider the endpoints of the subinterval. So what is your RS subinterval? That is basically equal to x r minus 1 xr. Okay, so this is our, okay, it is giving problem. Let me just, yeah. So this is the RS subinterval. What happened? Just a minute. So, oh. Yeah, I think it is visible now, right? The slide is visible?
Yes.
Okay, okay, thank you. So this is the RF subinterval and R is taken from 1 to n. Right, so these many subintervals we have, into which we have divided the closed interval AB. And now from each interval, r is varying from 1 to n, we are either considering the left hand points of the subintervals or the right hand points. And there we are evaluating the function, and each functional value is multiplied by the length of the subinterval. So this is the definition. And then finally we take more and more number of points. That means we are considering the limit h tending to 0 as well as n tends to infinity. Okay, so these are the definitions which we have been using since our +2 levels. Okay, so now just let me state you that it is not necessary to take the left hand endpoint or the right hand endpoint. In fact, we can consider any point xi r from the interval delta r. Okay, and then we can form the sum xi r into delta delta r. Yeah, delta r is the length. Okay, just a minute. Control Z. HR. HR is equal to the length of the subinterval xr minus xr minus. And then you take the limit r will run from 1 to n, limit h tends to 0. What is your h? H is the max of HR. Okay, and if this limit exists uniquely, then it is called the definite integration of fx dx. And if we can think about the geometrical interpretation of this definite integral, it is basically gives us the measure of the area enclosed by the graph, enclosed by the curve y equal to fx, and the ordinates x is equal to a, x is equal to b, and the x-axis. So that region is given by this. Now what is the basic thing over here? What is the basic idea? So we have two ingredients. Okay, the one is the region of integration, and a function is defined in the interval. Then what is the basic procedure? We are dividing the region of integration into finite parts first. And from each part we are taking a point, and at that point we are evaluating the value of the function, and that value of the function is multiplied by the length of the subinterval. This is my element, and then we are forming the sum for each interval, this element for each subinterval, and then we are adding all these elements and finally considering the limit h tending to 0. That means we are introducing more and more points within the subinterval so that the average length of the subintervals tends to 0. And in that limit, if the sum exists, okay, exists uniquely, that is called the definite integration. Okay, so this is the basic idea. Now, if we want to translate this idea for vector functions. So this is our objective, and what we do, what is our basic ingredient over here? Our region of integration now changed from closed interval.
Sir, one
It
doubt.
has been, yes.
Sir, in the previous slide where you mentioned xi-r, so sir, xi-r is what, the average of the two endpoints of the subintervals?
No, not necessarily. Any point from this subinterval. You see, I have mentioned here xi-r.
So sir, meaning what is the benefit of writing xi-r instead of the previous definition?
Achha, so previous definition so this is just a result, and if you use the previous definitions, then problem solving will be easier. Okay, if you take the equispace interval, but this is more general definition. Okay, it can be shown in fact in terms of a theorem that instead of taking the left hand endpoint or right hand endpoint, you can in fact take any point from the subinterval. Then also it will converge to the same point or same value. So this is the thing. As far as analytical calculation is concerned, previous definitions are easier, I would say. Okay, so now the region of integration is a space curve. You see, line in space. Region of integration from closed interval on a line has been changed to a portion of or a finite part of a line in space. And at each point on this line, a vector function is defined. Instead of a scalar function fx, at each point on this line, a vector function a is defined. So basic ingredients have been changed, but we are trying to implement the same idea for defining the line integral. Line means it is a line in space. It may be a straight line or it may be a curved line. Does not matter. Okay. So region of integration has been changed, and the function involved in the process, is a vector function now.
Sir,
That
your voice is breaking down.
this is breaking. Okay.
Sir, your voice is breaking down.
Okay, so that is internet, I think. So
It is clear, sir.
No, sir.
Sir,
It's
clear,
clear.
sir. You are audible.
Sir, it's clear.
yeah, that means the channel. The channel, some
Yes,
of
sir,
the
you are
networks are
audible.
tweaking.
Tell him
Yeah.
to rejoin, sir.
It is clear, sir.
Yes. So can you please rejoin? I can see, yeah, we have full strength in the network. Yeah, all lines are there. Yeah, so now what is the change? We are trying to implement the idea we have learned in our for one-dimensional function. The region of integration now is a space portion of finite portion of a line that is confined in a space, and it has been shown by this picture over here. First point, one terminal point is A and the other terminal point is B. And at each and every point on this curve, a vector function capital A is defined. So that means if you take, for example, if this point is say P1 is equal to 1, 1, 1, this point, then you have a definite vector defined, unique vector defined at that point, which is given by A evaluated at 1, 1, 1. In general, this vector A is a function of x, y, z. Okay, and at each and every point on this curve, which we call a line, in general, which is curved one, but the definition is valid for straight lines as well. Okay, so we divide the curve into finite parts by introducing some points, n minus 1 number of points, p1, p2, p minus 1, pp, and then pn minus 1. And the starting point is p0, end point is pn. P0 is a and pn is v. And then what is the next step? What is the next step? If you recall the definition of definite integration as a limit of a sum from each. So these points will divide the curve into n parts. You have two terminal points and we have introduced n minus 1 number of points in between. So therefore, the entire curve is divided into n parts. We have n plus 1 number of points in our hand. And from each part, we have to consider a point. Okay, so you look at every time you look at the analogy, from each point you take a point. From each part of the line, you take a point. So here we have considered the general line element, I would say, or general line element p1, p minus 1 to p suffix p. So this is the general element we have considered, and from this general element we consider a point, arbitrary point, not necessarily these should be terminal points. So any point xp we are considering. Then what we are doing, so at this point we can have the vector a. So this is a point and which is a function of x, y, z, and this point will have a coordinate, say xp, yp, zp, small xp, yp, zp, and at that point you calculate this vector because it is defined there, and then you take the component of that vector along the along the line pp1, along the line segment pp1 p PP. Okay,
Sir,
so
can you repeat
then,
again this?
okay,
Sir,
so
hello, sir.
yeah,
Sir,
I'm repeating.
sir, A vector is defined with respect to origins. Means what we have said that line integral of A vector. This is with respect to origin or with respect to the point A.
No. So it is defined on all points on the curve. So A is basically, let me just write over here. So function should be defined actually on the region of integration. Okay, so A, this vector A is a function of x, y, z. Okay, so therefore it is defined at P0, P1, P2, etc. Everywhere it is defined on this curve. And apart from this curve also it may be defined, but we are not concerned about that. Okay, so then we are focusing on a general element. So what we have done, like previously we used to divide the closed interval into finite parts by introducing the points x1, x2 up to xn minus 1. And along with the terminal points, we used to divide the interval into n parts. And this is a general element. So yeah, so this general element let us consider. And then from this interval, so from this element actually, from this line element, we are considering any arbitrary point, which is denoted by xp. This is an arbitrary point. Let us suppose xp has the coordinates xp, yp, zp. These are the coordinates. So therefore, as axyz is defined on this curve, so what we can do, we can calculate this vector. xp, it will be a constant vector, yp, zp. So therefore, let us suppose this is your vector. This is your vector A calculated at xp. Then what we'll do, we'll take the component of this vector along this line segment. Along this line segment, along this line segment, this. Okay, so which has, so p minus 1, let us take this pp vector. This is equal to delta r vector. And it has three components, delta xi plus delta yj plus delta zk. So along this vector, let us take the component of A calculated at the point xp. And then you multiply the length of this interval with this. Then what we will get? We'll get basically A calculated at xp, yp, zp and dot delta r. Okay, so you see whether you agree or not. So what we are doing, we are introducing n minus 1 number of points between A and B. And these n minus 1 number of points will divide the curve between A and B into n parts. Okay, from these n parts, we are considering a particular part of the curve. And from that particular curve, we are taking a point, xp. And there we are calculating the vector function. Now we don't have x apex. We have a vector function defined there. So that vector function we are taking, and then we are taking the component of that vector along the line segment pp minus 1 pp. Okay, so that component, and then we are multiplying that component with the length of this line element, which is delta r. So therefore, if you take the dot product of this, you will get the relevant quantity. That means you will get A delta r cos theta. So A cos theta is the component of A along the curve, and delta r is the length of the element. Okay, A cos theta is the component of A along the line segment, and delta r is the length of the line segment. Okay, so therefore this is my integration element, if you can connect with the definition of the function, integration of a definite integration of a function of single variable. Okay, so there we used to consider divide the interval into finite parts, and from each part we used to take a function point. We used to take a point. You look at this definition, and there we used to calculate the value of this function. And then, hello.
Mute that person. Mute person.
Sir, mute.
Sir, can you please mute everyone in the meeting?
Okay. So you look at this definition. From rth subinterval, we considered a point xi r, and there we have evaluated the value of that function. That was a scalar variable, a scalar function, and then that value is multiplied by the width of the subinterval. This is my integration element, and we take the sum over all such elements from each subinterval, and then we take the limit. If this limit exists, it is called the definite integration. So same idea, only the region of integration has been changed to a curved line in space, and here also we are introducing n-1 number of points, and eventually we will make n tends to infinity. And in a general element or general pth element of the curve or the line, what we are doing, we are considering an arbitrary point xp, and there we are calculating the vector function, which is the function involved in the integration process in this case. And then we are taking the component of this along the line segment, along the rth line segment p minus 1 pp. Okay, and that is basically a cos theta. Theta is the angle between the line segment pp minus 1 pp and the vector a. So therefore a cos theta is the component of the vector along this line segment. And what is the length of the line segment? Which is delta r. So this is the thing, and it can be written as the dot product of the vectors a calculated at this point and dot delta r. So both of these are basically same thing. Now you do the exercise, or you find the integration element from each of the subintervals, for each of the elements, and these are given by a dot delta r, and then you take the sum from p equal to 1 to n over all the segments, and then you finally take the limit delta r tends to 0. Yes.
Sir, what exactly does this integration of a vector dot dr vector gives? Like, for example, in the line integral, that integration would give us the area. So in this case, like, are we tracing the length over the curve from A to B?
No. So it depends actually. I will tell you. I will come back to that point. It will depend on the vector A. Okay, so this definition is purely mathematical at this moment. At this moment, this is mathematical definition. And if this limit exists uniquely, it is called the line integral of this vector function A over the curve C. Okay, curve C means this curve is named as C. This curve is named as C.
Meaning, like,
Now,
how in
in general,
line integral,
yes, please.
like how in line integral in the first definition you had written, we divided into those rectangular strip, and then we find the net integration as the sum of those individual strips. So how can we visualize it similarly for this part?
So you can visualize this very well if you take that A is a force field. A is a force field. If A is a force field, then F dot dr. Oh, can you please
Sir,
mute?
mute someone.
कौन है भाई म्यूट कर लो प्लीज
Sir, mute.
So mute.
Mute हो, thank you.
Yeah, so if A, this vector field is in particular a force field, then what does this F dot dr represent? This represent the work done by the
Potential.
force. Yeah, work done by the force F in moving a particle from the initial point to the terminal point. So therefore, this line integral, in that case, if A is a force field, will give us the work done by moving a particle from the initial point A to the terminal point B along the shown curve C. Okay, and if A is equal to 1, this A vector is basically is equal to the unit vector or 1 scalar vector, scalar function 1. Then probably you will get 1. Can we constant vector? If we want to find the length of this curve, probably this will not work. You need unit vector. No, this will not work. We have to introduce scalar integration in that case. So that will not come. But if you consider A as a force field, then you can understand a physical interpretation of this line integral. But later you will learn that in case of fluids, if A represents a vector, velocity vector, A represents the velocity vector, then if v dot dr, velocity A dot dr, this line integral will give us, and C is a closed curve, okay, give us the circulation. It has a different meaning. I will come back to that meaning when I will define curl of a vector. Okay, but at this moment, this definition is mathematical, and depending on the nature of this vector, you can draw the physical interpretation, or we can understand the physical interpretation of this line integral. And one particular example is that if F is a vector, is a force field, then this will basically represent the work done by the force field in moving a particle from initial point to the terminal point. Okay, so at this moment, this much I can say, and I will illustrate this with more examples when I will introduce the other concepts, other necessary concepts as well. Okay. So therefore, basic idea is
Sir?
similar, and yes. Yes.
Sir, why we use dot product in line integral? We want to project A vector over delta R vector.
Yes. So this is one type of line integral. Note that this is not, there can be other type of line integral. The basic thing is that you have to involve the vector in a way which may be useful to explain some physical quantity, like say work done, as I mentioned. Okay. Instead of considering the component of this along this, you could have maintained with the vector itself, and then you could have multiplied with delta R. That could have been your line integration element, but this is one type of line integral, and this is very common actually. Yeah, so someone was trying to ask something.
Sir, is A vector a unit vector? AXP vector?
Then?
Sir, is it a unit vector? Because then we are already taking dr vector, which may not be a unit vector.
No, they are not a unit vector. It is not necessary. So we are taking the amplitude of it in the definition. You see here, it is not one, and delta R is the length of
A vector.
A vector is the magnitude of this vector, and this angle is theta. This angle is theta. Yes, A cos theta is the component of A along delta R. A cos theta is the component of the vector A along delta R, and this delta R is the length of the subinterval. Okay, same idea, just translating into.
Sir,
yes.
Sir, what you are defined that integrations of A dot dr, this can be the volume. Means the when we define the curve, like we have to assume a 3D curve, and we have to differentiate with a dr vector, then that can be give us the volume also.
No, this will not give you the volume. Surface integral sometimes can give you volume. So
then sir, what is the then sir, what is the requirement of vector instead of scalar? we
requirement
can
of vector. So if you want to calculate the work done, suppose a particle is moving from one point to another point in space following different curves. Okay, you know the force field. So F is given. So a particle is moving from one point to another point following various paths, and in each case you want to determine the work done. Then this is the only way. This line integral is the only way, and not necessarily the work done will be same if the particle follows different paths. If it is same, then the force field is called conservative. Probably you know. If the work done by a particle in moving a point A to another point B following different paths, if the work done is same in all the cases, then the force field is conservative, like gravitational force field. But in case of other force fields, it may not be conservative. If there is friction involved in the process or other things, the field may not be conservative. So therefore, in that case, the work done by in moving a particle from one point to another point in the space following different paths will be different. Okay, in that case, we have to use this line integral to calculate the work done. Okay, so there are other quantities as well, because you don't know those terms, probably vorticity in case of vorticity in case of fluids, etc., velocity field, etc., momentum transport, etc. So momentum transport will not be the case, but integration along a streamline, okay, integration along a vortex line, etc. So in those cases, these line integrals will appear. But the definition, mathematical definition is this. Okay, this is the just the generalization of the definite integration for a function of single variable in 1D. Okay, so this is my point, and I will give you more examples later on. Okay, at this moment, just work done. A is the force field, and this line integral give us the work done in moving a particle from A to B following this given curve. And in this case, line integral can be defined by this limit of this sum. Okay. Hello.
Yes, sir.
Yeah, are you convinced with this definition? This is one kind of line integral. You can define another
yes, sir,
kind of line integral.
Mathematically, sir, convinced. But
Physically,
Practically,
you
sir, it
consider A
depends
is equal
on
to
vector.
force field.
Means what we are going to get, means it depend upon vector.
Yeah, it depends on vector. Correct interpretation. If it is a force field, you will get the work done. If it is different vector field, then we have to think what vector field is this, and depending on that vector field, we will get the interpretation. Okay, so this is the thing. Well, so then this integral is defined, denoted by A dot dr, and dr. This is a vector differential. It has three different components: I dx, j dy, k dz, and it can be in scalar form. It can be represented as this. Okay, so now we have the examples. Evaluate A dot dr, this line integral, A dot dr, and where A is a two-dimensional function, x square y square I plus yj, and the curve C is the parabola. Y square is equal to 4x, and along the parabola we'll move from the point 0, 0 to 4, 4. Okay, so along this curve we have to find the line integral. Okay, so let me discuss this example, and then I will stop today. Y square is equal to 4x. This is the parabola vector I will write. So what is the curve? Let me just go to the two dimensions. Y square is equal to 4x. So for each x we have two different y, and we have this type of graph of more or less.
Sir,
4x.
here
X.
x and y are separate.
Please repeat.
See, here, sir, x and y are both separate and they can be easily done without, say, drawing any other things.
Okay, let me just show you the curve C actually. So it will start from 0, 0. And then what is the other point?
4,4.
4,4.
So 4,4. So that means if we take x is equal to 4 and y will also be 4. That means we are following the upper branch. So if this is your 4, 0, then this is the point B actually, having coordinates 4,4. So this is your C. And x is moving from, x is changing from 0 to 4. And we have y square is equal to 4x. So therefore dy dx now, they are not independent. They are connected. So if you differentiate this, you will get 2y dy is equal to 4 dx. Okay. Now what is the vector involved over in the process? A is equal to x square y square I plus, let me just check. Let me just check yj. Okay. This is the vector plus yj is the vector. And then we have to find 0 to b a dot dr, and this is equal to, in Cartesian form, 0 to b, o to b basically is equal to a1. That means x square y square dx plus y dy. Okay.
Sir,
Yes.
264, sir.
Yes, sir, 264. Sir, we are replacing y square with 4x in the dx part, and y dy is 0 to 4.
Yeah. So we are moving along the curve. So we are moving along the curve while integrating. So therefore we have the liberty to replace x as y square by 4 or y is equal to 2 root x. So these are two possibilities. So any one we can use over here, and dx. So either we can write everything in terms of x or we can write everything in terms of y. Okay. So y square is equal to 4x. So which
Sir, it
one
will be easier in terms of x, sir, if we represent y in terms of
Y
x.
equals to 2 dx, sir.
Yes, sir.
Y
dy
equal
equals to 2 dx.
y
Then
dy
y square
equal to, yeah, y dy is equal to 2 dx and y square is equal to
4x.
and x will vary from 0 to 4.
4. Yes, sir.
And y square will be is equal to 4x cube dx, right?
Yes,
X
sir.
cube dx, and y dx will be equal
2
to
dx.
dx. So
Plus, sir,
therefore
plus.
2 dx plus, yeah, plus. So if we take common 4x cube plus 2 dx, that is equal to 0 to 4x cube plus 2 dx. So now life is very simple for us. X to the power 4 plus 2x, 0 to 4, and it turns out to be equal to 16 into 62, 56, I think, plus 8. 264 answer. Okay, so the first problem was quite simple. Now you consider the second problem. Here the curve C is given in parametric form in the first case. So A is the vector given by 3x square plus 6yi minus 14yz j plus 20xz square k. And we have to find this integral C. And C is the curve in the first case. We are moving from 0, 0 to 1 actually. 0, 0, 0 to 1, 1, 1. Following this curve, x is equal to t, y is equal to t square, z is equal to tq. This is the parametric form of the curve C. So Let me just write 3x square plus 6yi. So what is the vector involved in the process? A is equal to 3xy square, or 3x square plus 6yi. 3x square plus 6yi is the vector function minus 12
14yz
14yz. Okay, j, and then
20xz square.
20xz square k. 20xz square k. This is the vector. And what is the line? Line is defined by x is equal to t, y is equal to t squared, z is equal to t cube. Shape of this curve we are not worrying about. The essential thing is that we have to move to 1 1 1 following this curve. Okay, so in space we are moving from the point, so 0 x y z, and this is the point, say 1 1 1, and we don't know the shape of the curve. In this case, for example, had it been x is equal to sine t, y is equal to cos t, and z is equal to 0, then we know that that is a circle or a portion of circle on xy plane. But in this case, shape of the curve we don't know, but we have the parametric equation. All x, y, z, the coordinates on this curve are represented in terms of a third variable t. And for this point, what is the value of t? 0 0 0. What is t?
0.
It is 0. And for
0.
the second point, what is
1.
the value of
Just
t?
one.
1.
T1.
T equal to 1. So therefore, we'll move from the point 0 0 0 to the point 1 1 1 following this curve, as the value of t will move from 0 to 1. That is our observation. And from this also, we can easily deduce that dx is equal to dt, dy is equal to 2 dt,
2 dt. 2t dt.
2t dt,
2
sorry,
dt, sir.
and dz is equal to
3t
3t
square
square
dt.
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 Okay, so now we are in a position to evaluate this integral along the curve C A dot dr, and this is equal to, you tell me the components.
0 to 1.
No, C, at this moment I am writing C. Tell me the
Oh,
first
okay,
component
okay.
of A.
3t
3x
square
square plus 6y
3x square
plus
plus
6y
6y
6y dx plus minus, I think
minus
so,
minus 14y
yz
dy
dy
Well,
plus
plus
20xz square.
20xz square
dz.
dz. Now we will
Sir,
replace everything in terms of t.
sir, answer is 11, sir.
The answer is 5.
Sir, answer
11.
is 5, sir.
Oh,
5.
so you make the correction. Maybe
Sir,
there is a minor
can we
typo in
make the
one of
dy
your
and
calculation. So
sir,
x is equal to t. So therefore 3t square and 6y, that means 6t square.
60.
And what is dt? Dx dt.
dt.
Dx is dt minus yz. Y is t square and z is t cube. So
T
t
to
to
the
the
power
power
5.
5, 14 t to the power 5, and dy is equal to 2t
2t dt.
2t dt. And this is 20t to the power 7
7.
into dz is equal to 3t square dt. So everything we can simplify now. 0 to 1, 9t
5, sir.
square, 9t
9t
square.
square minus
In last it should be 9. 3t whole square.
This is
28 t to the power 6.
28 t to the power 6, and this one 20 plus
plus
60
plus
60.
60
9.
t to the power 9.
dt, and you can evaluate it easily. Okay, so therefore
5, sir.
the thing is that either we have to, most of the cases we have to use the equation of the curve, space curve or the line, okay, to convert the integral in terms of a single variable. So this we will do every
Yes,
time.
sir. 5, sir. Answer is 5.
It is 5.
5. Yes, sir.
Yes, sir.
It's a 5.
Yes, sir.
Okay, so correct. So I think you have got the idea. So now in the second part, so today I will leave. For the second part, what is the line? What is the curve C we are following from to reach from 0, 0, 0 to 1, 1, 1? We are following a different path. First, we are moving to the point 0, 0, 0 to 1, 0, 0. And
We will
then,
break the integral here, sir.
yeah, so we have to break the integral into different parts. And for each part, we have to use the information actually. For example, as we are moving from 0, 0, 0 to 1, 0, 0, following a straight line, we are moving along x-axis. Okay, we are moving along x-axis. I will show you later in the next class. So there, y and z are not changing. Therefore, dy and dz
So
they
we can
will be equal to
substitute
0.
y is equal to x square and z is equal to x cube.
So
And like this, we can separately evaluate for different dx, dy, dz.
different parts, and then we will add. Okay, so
Yes,
these
sir.
two I will show in the next class, and third one I have I will leave it for you. Okay, to try to solve this, and if you can solve part B and part C, that is also fine.
So the third one is an ellipse, sir. Say in the XY plane.
Yeah, it is an ellipse, and
Yes.
we will move from 0 to pi. T will move from 0 to, so half of the ellipse.
Yes.
Actually, first and second quadrant. That portion we will consider over here.
Yes, sir. Vertical ellipse, sir. Vertical ellipse.
Yeah, vertical ellipse. B is larger.
Yes, sir.
Okay,
Sir, we
so
have next class in 2 minutes after. After
please.
2 minutes, we have next class, sir. Can we leave?
Yeah, you can leave. So let me stop here today.
Please upload the slides, sir.
Yeah, I
Thank
will
you,
do
sir.
it. Do it definitely. So I am using the same file name, lecture1.pdf, and I am modifying it every day. Okay, after every class.